believe in science. We believe science can bring solutions to many of humanity's challenges.
How we can popularize science, how we can help science, we have to do something to make it easy for people to digest, to get involved with science. We can merge arts with science.
The work we do to protect communities from cyber threats is just a part of the work the global scientific community is doing to protect people from disease, enable technological progress, and through education to allow people to live fuller and more enjoyable lives.
Some kinds of discoveries can only be made through collaboration of very large numbers of people who bring very different talents to the problem. So science education throughout our society is the key to properly using science and employing it to solve problems.
Please welcome our host for today's discussion, David Eicher, an American editor, writer, and popularizer of astronomy and space. He has been editor-in-chief of Astronomy magazine since 2002. He is author, co-author, and editor of 21 books on science and American history. David Eicher.
Well, thank you very much and welcome. We have a big topic to tackle tonight, but not too big a one. Life in the universe and what it might be and where it might be in lots and lots of ways, both simple life and complex life. I'm Dave Eicher, editor of Astronomy magazine, and I'm a member of the Starmus board, and it's a real pleasure to be here with you tonight and to have all of you joining us on the stream as well. We're going to have about 45 minutes or so of discussion with two great minds, along with a lesser mind, mine. And you can also submit questions via Slido with the hashtag Michel Mayor. And I think there's information online about how to do that, and we will take a few questions in the last quarter or so of the program. So, without further ado, I'd like to introduce two good friends of mine who are very closely associated with Starmus, especially the first one, because Garik Israelian is an astrophysicist at the Institute of Astronomy in the Canary Islands. His specialties are across a number of interesting fields: extrasolar planets nearby us in the galaxy, the relationship between supernovae and black holes, massive stars that explode and become stellar black holes, and a number of other areas. He's a great guy, and he's also a musician, and that led to him getting interested in music very early on and befriending a guy who's really special. And together, the two of them, Garik and Brian May, who's an astronomer, he also has a day job as a guitarist, you may know, they co-founded the Starmus Festival, and we need more of this in our world, celebrating science and reason, getting together, getting along with all of our species on the planet and promoting our education and our knowledge of how to make the world a better place. So we're very happy to have him here, the founder, the director, co-founder, the director of Starmus. He's also written 30 papers or so, along with another guy I'm going to introduce, and he's a co-winner with the other fellow of the Victor Ambartsumian Prize in Astronomy. Very well known for his research on nearby planets in the galaxy. Please welcome Dr. Garik Israelian. Garik? How are you, pal? Hi. Good to see you. Now, a good friend and a close collaborator of Garik's is a very well-known guy who's a principal authority on extrasolar planets. He is an emeritus professor at the University of Geneva in Switzerland. And he is, among other things, very well known for discovering the first exoplanet, the first planet outside our solar system orbiting a sun-like star. This was in 1995. It's 51 Pegasi b. He won the Nobel Prize in 2019 for this discovery, shared it with a couple of collaborators. He has written many papers along with Garik and others about exoplanets. We now stand, all these years later, with about 5,500 extrasolar planets we know of orbiting in about 4,000 star systems. So we're getting a good sort of grouping of understanding the planets that are mostly relatively near us in the galaxy. This guy is a legend in his field. He's a wonderful man, brilliant guy. Please help me welcome the Nobel Prize laureate, Michel Mayor. Michel? Michel, how are you? Gentlemen, let's have a seat and let's talk planets for a little while.
Yes.
What do you say about that? There's a lot to talk about, and we have to solve the entire mystery of planets in about 45 minutes. So we know of, conservatively, about 10,000 billion planets in the universe, and that's just the visible universe. The universe could be much larger than that which we see. We know that chemistry is uniform throughout the cosmos through spectroscopy. So we also have samples that have now been returned. For example, going back a little ways, the first comet sample returned to Earth contained glycine from the comet Wild 2 that was returned by the Stardust spacecraft in 2006. So the stuff of life, the organics, are out there. But the distance scale of the cosmos is incredibly huge. It's very, very vast, even in our solar system, let alone to other stars. So we've been thinking about this for a couple thousand years, back to the Greeks. Guys, what about the existence of life elsewhere in other places in the cosmos? Where do you think we stand in a kind of a state-of-the-art moment where we are now thinking about life in the cosmos?
So it's always so strange to imagine that already more than 2,000 years ago, people was already discussing the problem of the plurality of worlds, and still more, the plurality of possible life in other places in the universe. So it was not exoplanet, it was a philosophical discussion of other worlds. But today, we have proved that at least the first part of the sentence, we have proved that we have many, many planets. Probably the best estimation that every star should have a planetary system. So this was discovered almost 30 years ago, but right now we have more than 5,000 exoplanets, so it's huge. This is extremely common. And we can ask the question, why you continue to search planets if you already have 5,000? It's simply that we have discovered what is called the diversity of planetary system. They are not similar to the solar system. They are extremely different. You have incredible objects. For example, you have planets orbiting so close to the star that the silicates, the rocks, are melted. So it's lava planet. A little bit further, you have ocean planet made mostly from water, and so on. You have gaseous giant planet, Jupiter, and so on. You have an icy planet. And what is probably closer to the discussion of this night, you have rocky planet. We start to discover planets made from rocks. And this is absolutely fantastic. Also, not only the parameters of the orbit are quite different, but from hours to decades, but also some. Okay, in the solar system, all the giant planets are orbiting almost on circular orbit. But what we have discovered, sometimes we have planets like this, with extremely elongated. So we are far to have understood completely the formation of planetary system. But the next question is, now, do we have the possibility to discover planet with conditions suitable for the development of the complex chemistry of life. And this is typically the reason of this discussion. What is the status? What we can dream to discover? What is the difficulty? What kind of instrumentation and so on? And then the next very more difficult question, do we have the capability to discover planet with technically advanced society? And this is a problem of intelligent life in the universe. So this is the goal of this question, this discussion.
Yeah, I would simply add that we know the famous Drake equation, which gives the probability of different processes up to the formation of life and then formation of intelligent life, right? And I think one of the key parameters in this equation, which has been clarified the last 50, 60 or 100 years, maybe less than 100 years, is that star formation of chemical elements, which are ingredients of life, and planet formation process are universal, which means in our galaxy, in different galaxies, and everywhere we are talking about same physics, exactly the same physics for forming stars, planets, and definitely molecules, and the most complex molecules. So we know the ingredients to form life are common in the universe: carbon, nitrogen, oxygen, CNO, etc. So, and these are the most stable and easy-forming molecules. So naturally, they will be common everywhere. All planets should have water in the form of ice or water vapor, whatever, because it's a very stable molecule. And then they will have methane, they will have ozone, they will have carbon dioxide, everything. So I think it was a key knowledge which came very recently, 1,000 years after Greek philosophers were just imagining, oh, there is life in the universe, etc. Now we have a clear knowledge that these processes are universal. And no, we are not talking about one or two planets to harbor conditions for life, but we are talking about billions of planets, potentially billions of planets, which can have necessary conditions, liquid water, biomarkers, etc., to host life.
Yes.
Yeah. Maybe one addition to what is there. Okay, it's not the place to describe the detailed process to form planets. But at the middle of the last century, the middle of the 20th century, people realized that the formation of planets is a residue of the collapse of big cloud of gas like Orion Nebula and so on. So you form huge generation of planets with numerous planets and so on. So, and always you have an excess of rotation of the gas. So this is the origin of the disk of dust and gas to form new generation of planets. So planetary systems are simply a byproduct of the formation of stars. So this is the reason why we believe that we should have billion and hundreds of billions of planets in the Milky Way. Sorry.
Exactly, yeah.
Gentlemen, since the initial discoveries in the 1990s, principally yours, now we have a tremendous catalog of worlds orbiting other stars, mostly stars that are relatively near us in the Milky Way galaxy, but we're expanding outward. Now there are several thousands of such planets known. Could you talk a little bit, gentlemen, about the techniques? How do we discover these planetary systems? And what leads you with the techniques to go after certain kinds of planets that may be more of interest from that oldest of questions, perhaps, in humanity? Are we alone here?
So the first point we have to mention is the fact that let's imagine you are relatively far from the solar system and you look it with some instrument. And you have the sun and you have a small dot, let's say Jupiter, the biggest planet. And Jupiter is not producing luminosity, but reflecting only a small, teeny part of the luminosity of the sun. And the ratio is 1 billion. So immediately when you are at some distance, you are like this. Let's imagine you have a small light 1 billion times smaller than this slide. You have no chance to see it. So this was a difficulty to discover planet. And also we have to consider that planets are relatively small compared to stars. For example, the Earth is something like 300,000 times smaller, lighter than the Sun. So what we have used 25 more years ago is to try to measure the velocity, the change of the velocity of the stars. So if you have a planet orbiting like this, you cannot see the planet, but you can maybe detect the small wobble of the velocity of the star. So you need to build an instrument to measure extremely small change of the velocity of stars. So this was what we used to discover the first one, and then after we have discovered several hundred of planets and our colleagues in different places also. So this was the first technique. But as I mentioned before, we have discovered planets with extremely short period. When we say a short period, it signifies that the planet orbits the star extremely close to the star. So you have a good chance sometimes to have an orbit, an eclipse. So we are using the terminology of transit. So sometime when the planet crosses the disk of the star, you have a small decrease of the luminosity of the star. So this is a new technique, and this was absolutely fantastic technique because this technique was used to discover, I don't know, thousands of planets with different space missions. You have planet Kepler, Corot, you have a lot of different space missions, having provided a huge number of new planetary systems. And not only stars with one planet, but we have discovered a lot of stars with several planets. So you have one planet, a second planet, a third planet, and so on. So you have to disentangle this signal, and you discover it's a very complex planetary system. So this is typically the most, okay, you have other techniques, but these are the two most important ones. And what is very interesting, the Doppler techniques, the change of the velocity, give access to the measurement of the mass of the planet, but the technique of the transit give access to the size of the planet. So if you have the mass and the size, you can determine the density of the planet. And so we have direct proof that it's gaseous giant planet or rocky planet or things like this. So we can start to do physics to understand all this complexity of planetary system. And this was a direct proof that the 51 Peg, for example, is a planet, because still 4 years after, some people, some colleagues, was doubting that it was really a planet. So no, we are sure it's a planet.
Yeah. I will simply add to Michel's comment that the technique that has been used 30, 40 years ago, the Doppler velocity technique, is still the same. We're still considering a similar number of spectral lines for cross-correlation, 4,000, 5,000, 6,000 spectral lines in typical solar-type star to detect that. But the technology is incredibly different. Nowadays, we get to precisions down to 10 already centimeter per second. That's where we are, so we can detect Earth-like, nearly Earth-like planets, Earth twins. And that's all thanks to technology. Vacuum chambers, better detectors. Now we have an incredibly precise spectrographs working on VLT, etc. So the technology is actually driving this field in all different methods. It can be microlasing, it can be any direct imaging of planets. So using chronography, etc., adaptive optics. So as I always said, that astronomy is a technology-driven field. A lot, I would say. Technology makes a huge difference in a very short time scale, 20, 30 years, and you are already in a different domain.
Absolutely. And guys, you've collaborated on a lot of projects, papers together. You've shared the M. Bartsumian Prize. This is now moving in a slightly more interesting direction, this whole field. It's been a booming cottage industry ever since 1995, an explosively popular area of research. What is it that drives, help us to understand where we're preferentially looking. Can you talk a little bit about water? Why is water so important? Talk a little bit about habitable zones, perhaps, and temperature as a factor where you might look for and find more interesting planets that may yield some clues.
Yes. Okay. Life cannot be detected around gaseous giant planet, Jupiter, Saturn, and so on. Cannot be detected around extremely hot planet, and so on. So you have to, physics and chemistry put some limits. You cannot imagine what you want. And maybe one of the most important constraints of what is life is the capability to transfer all the information, how you exchange energy with the medium, how you evolve and so on, to your daughter, from generation to generation. So this is the magic of the DNA, the genetic code, that you can transfer to generation by generation all this very complex information. And this is a very long chain of molecules. And this, if you eat this chain, the DNA, above maybe 120 degrees, it will be broken. It is what you are doing when you sterilize aliments. To avoid the proliferation of bacteria, you simply eat, and this cuts the chain of life. You can also cool the aliments below -20 or something like this, because at this temperature, the chemistry is so slow that, okay, nothing interesting happens. So this is the reason why astronomers are looking for life planet, candidate for life development with a temperature between something like -20 to +100 something. This domain of temperature corresponds to the domain of the liquid water. And water is a perfect solvent to facilitate the chemical reaction. So when astronomers try to detect planet with water, is not because we like to have something similar to the Earth, because it's simply because it's the reason of physics or chemistry. So after we have to search if we can find planets similar to this. And today we have discovered quite several dozen of convenient planets. They are not perfect. Some of them are hosted by low-mass stars. So the habitable zone, the zone where you have liquid water, is quite close to the star, because this kind of star are not efficient nuclear reactor. So maybe we have some other difficulties. So today, some observatories, some people are looking to find maybe a planet a little in the habitable zone, but a little bit further. So, okay, right now a lot of people are doing this kind of job. It's not easy because I don't like to mention too many quantities. But you see, you have the sun, you have the Earth. This is a perfect planet at a good distance, but the planet will try a motion of the sun of only 10 centimeters per second during 1 year. So let's imagine you have the change of the velocity of the sun is something like this during 1 year. And you want to discover and to measure this kind of things. So this is a real present difficulty with kind of things. And also the transit, the technique of the transit is not so easy also, because the Earth is so small compared to the sun. So the deep of the luminosity, when you have the transit, is so small. It's 1/10 of a thousand of the luminosity. So you cannot do it on the ground because atmosphere is disturbing. You have to go in space. And it's possible, but it's not easy. So this is the background why you are not looking for result in 1 year.
Yes, I will simply add to Michel's comments that obviously this chain of chemical reactions to building DNAs, you can cut it easily, and it's very fragile. It's very fragile. But there are even more parameters that can cut this. For instance, magnetic activity of your parent star. Flashes, flares, super flares, those are potentially phenomena which can kill biological life in a short time scale. Not even talking about nearby supernovae explosions, which can really bring the flux of neutrons to such a high numbers that can destroy any biology forming on a planet. And so it's really a very fragile process to build a biological life. And if we are talking about plants and forming more advanced level of biosphere, then we need more even conditions. We need tectonics, we need volcanic activity, and to have tectonics, volcanic activity, we need radioactive nuclei, we need thorium, we need uranium, and those will come from a star. So unless we have radioactivity, we won't have a tectonic, because this is geoenergy, right? The geothermal energy, which is in Earth, it's 60% of geothermal energy comes from a decay of radioactive nuclei deep in the core. So we have lots of conditions that will very fragile to build life, biological life, and to detect life, biological life on other planets. Obviously, we don't. Michel mentioned these biomarkers, which is carbon dioxide, methane, etc. But there is also something which is called red age, which we are able to detect. This is a light which is reflected from plants, from chlorophyll, because apparently plants absorb optical spectrum, but they reflect infrared after 7,000 angstrom. And this is nature which has done to avoid a overheating of plants, because otherwise they will be destroyed. So everything above 7,000 angstrom is reflected. And you will see it in the Earth-shine spectrum. If you observe the Earth from space, you will see the forest. You will see Amazonia with a very sharp change in the spectrum at 7,000 angstrom. It's about 50% change in the flux. It goes from 10 to 50% due to the chlorophyll. And then we can detect this in other planets. We have now technology, I think even with James Webb, that we can go survey and detect the red age, which will be a very clear signal of forests and plants on a planet. Obviously, when there are no clouds, like in case of the Earth, right? So that's also a very interesting signal for detecting biospheres.
Maybe I will add a few comments. You mentioned the tectonic of plates.
Yeah.
The fact you have a motion of continents on the Earth. It looks completely disconnected of this question. In fact, this is part of one of the extremely interesting topics. Okay, we mentioned the fact that the temperature should be good for the chemistry of life, not too cold, not too hot. But to maintain this condition on a few billion years is far to be evident. At the beginning, the sun was 30% less luminous than today. So if today, let's imagine you decrease the luminosity by 30%, every ocean will be frozen. So happily at the time, you have a huge carbon dioxide content, 96% of the atmosphere. And this prevents the Earth to be frozen. But then after, you have a decrease of the carbon dioxide. And we are at risk to be frozen. But happily, we have the tectonic of plates, re-injecting continuously a small amount of carbon dioxide, and so on and so on. It's a fascinating story of the Earth to see the difficulty to control the temperature of the Earth during few billion years, not to stop the adventure of the life development. This is absolutely a beautiful aspect of the science, to touch this kind of difficulties and to see the magic of all these different processes able to maintain the temperature of the Earth, not too cold, not too hot.
Yeah, indeed, I totally agree. This is very interesting. The carbon balance on the Earth was one of the key parameters, actually. We're not talking about carbon dioxide increase during Industrial Revolution, which was, I think, 50% in last 300 years, right? And the methane was 150% increase, and that's due to the human activity. But there are also natural processes which try to refresh the carbon, which always take the carbon from the atmosphere down to crust and then replenish. Very interesting point. Thank you.
Garik, you've talked a lot about technology really driving a lot of our awakening to what we should be investigating in this field at a very rapid pace. With instruments that are there, with TESS, with the Webb Space Telescope, with others rolling out, do you have further comments about the clues? What should we be looking for that may be indicative of real interest in planetary atmospheres that are out there in the coming years, now and in the coming years?
Yes. How is it possible to measure the chemical composition of planets? Because this is absolutely a key point to detect what is mentioned, what is biomarkers. So I mentioned that you have this huge problem of the ratio of luminosity 1 billion. So how you can analyze the atmosphere of the planet without being disturbed by the huge luminosity of the star? So this is the help of the nature. When you have the planet crossing the disk of the star, the transit, the atmosphere of the planet will filter a little bit the luminosity of the star. So when you compare the spectrum of the distribution of the wavelengths before and behind the transit, you have a small difference. And this small difference is only due to the chemical composition of the atmosphere of the planet. So you have too big quantity, and the small difference gives the possibility to determine the chemical composition of the planet. Difficult, difficult, difficult. You need a lot of photons to do it. And right now, to rebound on your question, for example, Europe is building a telescope in north of Chile with a diameter, the diameter of the mind mirror of 39 meters. Let's say is much bigger than this room. This is a mirror. And the operation will start probably in 2008. The construction is working well. And so this will do a lot of questions, we try to solve a lot of questions in astronomy, but in particular will certainly contribute to the search of biomarker, chemical signature of life on planet. And evidently you have the James Webb Telescope, smaller telescope, but above the atmosphere, and it will do the same job. And for example, I discussed recently with one of the boss of the James Webb Telescope, and he mentioned that 30% of the time of this fantastic project is devoted to planetary system, exoplanet. So this is, at the present time, is really a major part of the astronomy, a big chapter of today.
Yeah, absolutely. Talking about James Webb Telescope, one of the key issues, key points of this telescope is that it will have the capacity to detect chlorofluorine carbides, CFCs. And there has been an estimate that with one-day integration, James Webb will be able to detect a level which is 10 times only higher than the Earth atmosphere on an exoplanet. So if we have a planet like the Earth, where the level of CFC is 10 times higher than in our atmosphere, James Webb will be able to detect that, which is already a technosignature, which is a signature that there is the artificial, most probably artificial origin of CFCs on an alien planet. It's one of the examples of technosignatures. There are some other technosignatures. We can talk about this now, but this is a...
And that's one of the ways that we could really begin to believe that we're really certain about a detection, would be something that's really, really abnormal compared to what we would expect from a natural planet.
Yeah, exactly. I think this is probably the key point of one of the key points of today's discussion. So how do you detect an alien civilization, intelligent life? Not just the biosphere, not just water, liquid water, etc. But how you can see, all right, so we have detected this, we have a search, we are doing a survey, or we suddenly detected something which signals alien life. This has been going on since the 60s and 50s when the Radio SETI project has started with Carl Sagan, with all this generation of science communicators and Frank Drake, etc. They from the SETI Institute. We know the whole story, right? But now, after discovery of extrasolar planets, we move to optical SETI. We are already talking about discovering laser emissions from alien life, which can be detected in the spectra of extrasolar planets or even maybe stars, where we have those planets. And so there are different technosignatures. And one I can highlight maybe is the idea which belongs to Shklovsky and Carl Sagan. They published a paper in the 60s, an idea that if you have an alien technologically advanced civilization, which is not very advanced, but it's at the level of our civilization, maybe a bit more. But what they will do with the nuclear waste, because you are producing so much nuclear energy, and the nuclear waste, you have to store it, and during thousands of years, you have a problem. And especially if you are an interplanetary civilization, like probably we will be in 100 years, moving between Mars, etc., so we'll be using a lot of nuclear fuel. So all that stuff, they were considering that the host star will be used as a repository for this, so they will dump all the processed nuclear waste on the surface of the star, which will be essentially plutonium-239, which is a product from uranium-238, is it natural uranium converted to plutonium-239, and thorium-232, which is converted into uranium-233. So both these reactions produce a lot of nuclear waste, which you dump on the surface of your parent star. And apparently, there will be a slow nuclear fusion going on the surface of your star, which will produce a couple of elements which do not exist on the surface of your star. Like neodymium, parasodymium, these are two elements, and maybe some other elements also. I think technetium was one of the co-products. Then if you observe the star and you see the spectral lines, it will be a signature that there was an extra source of nuclear waste in the surface, and that will stay there for millions of years because those heavy elements will virtually they will sink, but there were processes which will be working against this sinking. Anyway, this is a very complicated physics, what will happen with this. But can we detect those spectral lines today or not? That's the question. So for this, you need to review millions of stars, I would say. The first thing, and for those millions of stars with planetary systems, you will need spectra of extremely high quality, because we are talking about a couple of milliangstrom equivalent with very small, tiny spectral features. Which means the signal to noise has to be like 1,000 or more than 1,000, extremely high quality spectra for millions of stars. So I would say you need telescopes like in Chile, many of them. You need a lot of time integration to go for surveying millions of stars. And then even after do that, you need extremely powerful softwares, machine learning based softs to go and compare millions of stars, solar twins, to see all those signatures and the differences, etc. So the technology, we know what to do. We know it can be done. We will have all the algorithms, etc., but it's a matter of time. It's a matter of money, because you need to build all those telescopes. With only one ELT is definitely not enough. But we can do a couple of hundred stars, maybe 1,000 stars, but we are not going to survey millions. I'm not going to survey millions.
Maybe you consider my colleague to be a little bit... I don't know, too optimistic, yes. But I will just mention one smaller problem existing right now. A few years ago, Europe sent a satellite called Gaia, and measuring the position of stars, the motion of stars, and the distance of stars due to the small wobble. And 2 billion of stars. And the precision, the individual precision of one position is 50 micro-arcsecond. So you cannot say what is 50 micro-arcsecond. So 1 milli-arcsecond is the distance between 2 lamps on the moon. So let's imagine you have put 2 flash lamps on the moon. The angular distance is 1 milli-arcsecond. So 50 micro-arcsecond is the distance between 5 centimeters on the moon. And this is currently done for billions of stars in the Milky Way. So what you can dream to be completely crazy, in fact, today, instrumentation in astronomy are simply fantastic. But I have one question to ask to the people.
Yes.
If you allow me. Okay, physics is the same everywhere in the universe. So, okay, we are sure that you have a huge number of rocky planets at the good distance of stars with liquid water. This is absolutely not a question. So, at the present time, after this is a problem of biology. So, do we have a chance to develop life? Not intelligent life, but already life. So, I would ask to people believing that we have huge number of planets in the universe with some form of life. It could be unicellular bacteria, things like that. Not evolved, but simply life. People convinced that life exists in other planets can... Okay? And people convinced that we should not have life in other parts of the universe. Okay, the argument is very strong, so we will see in 20 years from now who was...
It's from Harvard. It's called Harvard.
Okay, sorry.
That's okay. Guys, we have just a few minutes left, and then we're going to take some questions. Let me just throw out briefly, if you could address this. I'm not trying to beat up on science fiction. We love science fiction, but in all of our science fiction, we have sophisticated beings with mass traveling here, there, and everywhere in the universe. And we have other beings that pretty much, for the most part, are bipedals, and they have 2 eyes in some way, shape, or form. Some of them even understand English. But I wonder if you could just address the incredible diversity, how different life could be out there, incredibly different than what we're familiar with here, but be alive, and the phenomenally huge cosmic distance scale. We're probably not going to have aliens, even if the universe is filled with them, landing here and having dinner with us tonight. But address this a little bit, if you would, these kind of conceptions that science fiction feeds all of us.
I like this question. Because, okay, let's imagine that in the coming few years, we will discover a perfect planet, rocky planet with in the habitable zone, with water at the surface, and so on. So let's say at 30 light years. 30 light years is really a neighbor. Okay. So you say, you start to dream to send, to go and to have real travel to visit this place here. But 30 years is 1 billion of second. So it's already 1 billion times further than the moon. And the moon is the place, the most distant place visited by people 50-something years ago. So a factor 1 billion is not a detail. It's not to say, okay, we have to take our time to go. It's completely crazy. They need 3 days to go to the moon. Light need only 1 second. So if you multiply 3 days by 1 billion, I don't know what is it, but it's too long. And what is, and okay, the optimists in the room say, okay, we can accelerate. But you know that when you want to accelerate, you have to pay the price, and you have to put some energy to do it. Where you want to put this energy, to take this energy during this travel? It's completely impossible. So the dream that maybe if the climate of the Earth start to be too bad for the humanity, the dream to emigrate to some planet is not possible. It's simply not possible. It's much too further. And evidently some people say, oh, maybe we don't know some complex new physics and we can do it. But okay, with the present status of the physics, we have no way to escape to this negative possibility to emigrate. Sorry, the Earth is not too bad.
Okay, let's move on to, we're going to take 3 questions here from viewers, and we'll see where we stand with them here from whoever wants to jump in here. Let's start with one here from Janka. How does artificial intelligence help the search for life elsewhere in the universe, and how might it help as we push on with AI technology? Or is the answer not much, based on Michel's face?
Yeah.
Yes, we have, okay. It's relatively technical, but the sun is not perfect. The sun has magnetic field, magnetic activity, and so on, spots, eruption, and so on. So when you try to measure the change of the velocity of star like the sun, you are only affected by this kind of magnetic phenomena. So the signal of the planet is embedded inside this huge quantity of noise. So at the present time, some people are trying to use this kind of new numerical technology to try to disentangle the noise due to the magnetic activity from the signal of the planet. It's a relatively small application, but...
Yeah, there are similar applications in spectroscopy, which is in my field, and dealing with many stars with lots of tiny spectral lines. Sometimes it's really difficult. You can't really go to theoretical modeling to find out, especially when it comes to turbulence and lots of physics which is hidden. It goes to straight-on comparison between millions of stars, and then you need really machine learning stuff to teach your software what is normal, what is 1 sigma not normal, what is 3 sigma not normal, and then it will review millions of spectra to see what is there. And not only this, I think there is a new field which will be developing very soon, which is in polarimetry, imaging of direct imaging of planets, even in transits of where imagine Earth. We are observing Earth, night part of the planet from far away. You see infrared spots on the surface, which are large cities, there's the Los Angeles and Mexico and Tokyo. There are really infrared spots on the surface of the Earth. So if you are talking about different planet which has cities, then those infrared inhomogeneities will be visible as a rotation of the planet going on. So you may have a similar thing from volcanoes, but then you have to make sure that you are not confusing volcanic activity with large cities like Los Angeles, etc. For this you need to do planimetry. And then because that can distinguish materials, it can say if this is and the same applied to the famous Dyson spheres. When you have structures around the planet, artificial structures to absorb the energy of the parent stars, convert it into electricity. So the planimetry will enable to see the geometry of that stuff, if these are debris, planetary, asteroids or whatever, or if this is an artificial structure. Then and to do all those things which we know how to do, they are talking about very small signals, extremely small signals with models. You need our AI-based, machine learning-based softwares to go and distinguish and separate artificial from natural, blah, blah, blah. So that's is a huge new field which is starting now, actually.
Excellent. Let's go to a question. This is a fairly common old question, but it's an important one, I think. This is from Peter. Could you comment briefly on the potential existence of non-carbon-based life? People talk a lot in stories about silicon and other elements and so on that are easy to that like to combine with things and so on. What do you think about that? And again, this gets back to, could life elsewhere be dramatically different than us? But what do you think about non-carbon-based?
Yes, it was explored by many people using the silicium. But if you are looking at the huge diversity of molecules based on the carbon and the molecule based on silicium, it's completely different. The carbon offers so many complex possibilities, so I believe it's not a good way to proceed.
I agree.
Excellent. Now, this one, this has to be addressed here. Can you tell us your best joke about astrophysics in this area of research? This is, I regret to say that this is from Anonymous, but that's all it is. Here, no, I'll go on. Okay. But seriously, here's another one that always gets asked, and this is from Victor. What, in your minds, what would the consequences be if we had a very confident detection of a planet? Maybe it's an atmospheric detection spectroscopically. What would this do socially on Earth? You know, we sometimes claim to be a civilization here, not so sure, but what would this do psychologically and socially and politically on this planet? You may not care to comment based on, okay.
This question was asked to Jill Tarter a couple of years ago at Starmus. And she said there was a survey in US asking people, do you think there is life in the universe? And it has been detected. She said that people were not surprised. They said, oh, so what? Because they are not so used to this. They see it every day in movies. They hear sometimes the UFO stories and everything. So they are already ready. And most of them will be quite skeptical. And some of them will say, so what? We knew that already.
we already knew this.
We already knew this. So I think, unfortunately, it won't make headlines. That will be something different.
This would be big in the news cycle for about 48 hours, and then the things would move on, maybe. Yeah, that says a lot about where we are, I think, here these days. But are there any final comments? Where is this field going compared to where it's been since your discovery, Michel? It's a I have trouble thinking of a more rapidly moving field within astronomy, astrophysics, planetary science. Where are things going now in the coming years?
We are we are living a very happy people because during 2,000 years, people was asking to answer to this question, and now we have the technology to give an answer. So it's fantastic.
One example, square kilometer array, SKA, today is able to detect radio emission from a planet like Earth, artificial radio emission, at a distance of a couple of parsecs. So we have today technology, already we have it. It's about building it in South Africa. SKA will be very soon operational, and it will have a sensitivity to detect Earth twin, which is a techno signature, basically, radio noise produced by a planet like the Earth. So we have it. But I'm not talking about spectra, blah, blah, blah.
Yeah.
Just SKA, which is operational today.
SKA is a huge
Square kilometer array. Yeah.
Yes, a set of radio telescope in the southern sky.
I always think they were talking to astronomers. Sorry, I forget it. Yeah, it's a square kilometer array radio telescope.
So that's just the immediate, very close celestial neighborhood.
Yeah.
But if we get that capability out to a few dozen parsecs, that begins to really awaken the technology to who knows
Definitely.
what. And,
Definitely. And SKA every day will produce more data, I think it was 100 times more data, than entire internet. Entire internet on this planet, SKA will produce more data. So we need extremely efficient algorithms based on ML, etc., to process the data. And I think IBM is building a special data processing center only to process data from square kilometer array. That's massive.
Here's another question. We got just a few minutes left now, but here's another question. Some news reports claim, an Earth-like exoplanet has been discovered over and over and over. Some magazines deal in truth and don't do that. Okay, I'm just saying. But how many worlds do we know that are approaching, that we might call them super Earths perhaps, that are terrestrial in our catalog of planets relative to, hot Jupiters and other types of larger worlds? Are we getting the capability to find planets that are maybe rocky, terrestrial, what we think of perhaps as friendly planets to the kind of life we are, at least?
Rocky planets are really difficult to find because it's a relatively small planet for us. So it's true that we don't have so many discoveries because we are in a domain of where discoveries are very difficult. But if we correct for the bias of detection, we know that we have plenty. So this is a big challenge for the present astronomer to continue to explore the domain of this low-mass planet. But we are really confident that it's not so difficult, this.
Here's an unusual one. I'm going to throw this out to both of you. You talked early on about the philosophy of science a little bit and where we're going with some of these discoveries. Do each of you have a favorite philosopher or philosopher of science who you think of? What drives you to hunt for these planets and think about this catalog of worlds that are out there and whether we might not be alone in this big mess? Does anything come to mind there?
I don't have a favorite philosopher, but I'm always very impressed by the fact that more than 2,000 years ago, some philosopher was already discussing these kind of questions.
Yes.
Very good.
And are not philosophers, but maybe sci-fi writers, definitely.
Yeah. Garik, how about, can you characterize a little bit, what are we learning about the numbers of planets in planetary systems as we find more planets, as techniques improve and we move a little farther out around us in the Milky Way? Is the solar system kind of usual or kind of unusual? Are there most planetary systems, going back to Laplace and others, would we expect to find, a dozen planets, something on that order, the way material accretes down to make a star and a bunch of other stuff? Any thoughts on that, the normality of where we are or what we're finding out there in the catalog of exoworlds?
Yeah. So this diversity of planetary systems that we know today, so all sorts of planetary systems with any kind of distribution of mass and angular momentum around stars, it comes from initial conditions when you form planets, and it's a semi-random process. This planetary billiard, where you start building with the runaway accretion of giant planets and the small ones, and they have to survive, and there are collisions, etc. So virtually, it's not completely random, but it's a semi-random process. So that's why we have this huge diversity. I think we have dozens of planetary systems which look like our solar system, dozens, out of several thousand, which, I mean, if you are talking about billions of planetary systems in our solar system, it means hundreds of millions of planetary systems like our solar system. So, but I don't think for forming life you need exactly the system like our solar system. Although there are people who claim to form life, you need a giant planet like Jupiter, because it will attract all the asteroids which are coming towards the Earth to save Earth from impacts of giant asteroids. So probably it's good to have a giant planet in the system as someone to save us from
a vacuum cleaner.
A vacuum cleaner, exactly.
Yeah.
So probably we need this.
Very beneficially.
Yeah.
Is the inventory of exoplanetary systems that we're putting together now, is this just another lesson in us, in the long history of us finding out that we're not so special after all?
Right, yeah. The models of formation and evolution of planetary systems, they show that changing a bit parameters, you start building all sorts of different planetary systems. That's very interesting, right? So, which means the physics is extremely sensitive to very tiny processes. And I can count like at least 10 parameters, if not more, that will control which kind of planets and how many planets will be forming around the star. So the initial conditions of a dust and gas ratio, which is more or less constant, but not exactly, and the angular momentum of a star, which is also a very, very critical point, and chemical composition, chemical makeup, even a location. So all these parameters will virtually decide the diversity of planetary systems, which we will not be surprised. I mean, I'm no longer surprised when we discover this or that planetary systems. I said, all right, okay, so what? Yes, we have one more system which is different from the rest, and we need models to,
I wonder if you have any thoughts, Garik, on a day, neither one of us is quite that old, but 2.6 billion years ago, the so-called the Great Oxidation or Great Oxygenation event, when microbes began to produce a lot of excess oxygen on Earth, really transformed this planet in enormous ways. And maybe this gets back to what you're looking for in a biosignature, but is it inevitable, do you think, that a living world becomes dramatically different than a non-living world?
Maybe, I don't know. I don't know. That's a very, very hard question.
Sorry. Okay.
Yeah.
Very good. Well, let's see if we have another question or two from the audience. You mentioned we already have potential planets with good conditions for having life. Can we send probes there to check them? Well, I don't know if you have any thoughts on, probably most life in the universe, well, we don't know, but it's probably simple life, microbial life. And the JUICE mission now is underway, and there are, exotic and interesting moons in our solar system, Europa and Enceladus and others. Do you have any thoughts on exploring the solar system and possibly finding microbes, whether it be from JUICE or other missions, as an early step long before perhaps we get to discovering other civilizations, if you will.
Let's repeat maybe the question for Michel. Yeah.
Are we on the precipice of really making some interesting progress, possibly finding microbes in our solar system, whether it be with JUICE, in the Saturnian system, or moons in the Jovian system, or even subsurface aquifers on Mars or other places? How common do we think microbes might be in hardy conditions?
We have discussed mostly the problem of the possibility of life on exoplanet. Let's imagine in a couple of years, 10 years, decade, I don't know, we have a relatively strong proof that life exists in other parts of the universe. So this is already a very strong philosophical answer. But I'm a really enthusiast of the potential of the space discoveries in the solar system. We know that a satellite of Jupiter, Europa, have an ice shield. So an ice shield is not a glacier. You have a liquid water below, an ocean, and sometimes due to some change in the orbit of the satellite, you have some crack in the ice shield, and some water is going up and immediately froze here. So this is observed by spacecraft. Let's imagine in the future, it is not a fantasy. You send a mission, you pick part of this excess of ice. This ice is coming from below. So you melt it, you filter, you analyze. Let's imagine if you have the chance to detect some unicellular form of life. So this will be absolutely fantastic, because you will have the possibility to see if the DNA of this organism is the same or not to the Earth. So is the receipt of life is universal or not? Because we know the chemists have the potential to build some helix form of molecules of different kind of geometry and different composition. But we don't know if this kind of things is really used by different places of the universe. So the potential of the research related to the question of life is huge in the solar system itself. And this is Europa, but you have also Encelade. Encelade is a satellite of Saturn, and we have observed that time to time you have geyser going up to 100 kilometers on top of the surface of Encelade. So if you have a spacecraft going through this jet of the geyser, you can do some analysis and see what kind of water it is. We know it's a salted water, but do we have something interesting inside? So the potential inside the solar system is absolutely fantastic. Next generation.
The theory of migration of life in the galaxy is very old, actually. It was Fred Hoyle and many others were talking the viruses which can survive minus 180 degrees, and there are complex organic molecules which we observe already in interstellar medium, very complicated molecular structures. So the probability that they can move from one stellar system to another and move in the galaxy is very high, actually. It's very high.
Yes.
But they should survive.
Yes, this
cosmic rays.
The problem of the panspermie is not so easy of evolved form of life, because some of my colleagues in Lausanne have done some experiment with bacteria. So if you have a gun, you put on the bullet some kind of very rare bacteria. Then after you shoot in some place where it's relatively slowly, and then you analyze. And despite the huge deceleration, the bacteria survived. So, then they have made the same experiment with ultracentrifuges instrument, and with arriving to 1 million of G. So huge acceleration, and despite the fact the bacteria survive. So this is a good argument to say maybe you have the possibility to transfer back a form of life from Mars to Earth. So this is probably possible. But to go further, it's much more difficult, because after you have a change of the chemical properties of life. So racimisation des acides, I don't know. And so probably from one one planetary system to another one, I believe it's not possible. And I'm attending time to time some conference on exobiology, and this is not a piece discussed by people.
Yeah.
No, the Earth is already so complex. We have not to put the question in other part of the universe.
Alas. Garik?
No, yeah, I agree. It's very hard. Especially they have to survive cosmic rays.
Yeah.
High flux.
Yes.
And it's...
Which even the health of an astronaut going to Mars, that short distance is a little bit of a, but that's for another time. We've only been thinking about this question for a couple thousand years now, but we had a good hour. Thank you, guys, for the great discussion. Dr. Garik Israelian, Professor Michel Mayor, great friends and heroes of us. You've been a wonderful audience. Thanks for coming and turning out. Great questions. And thanks for caring about things that we think are really important for us as people trying to have a good time living down on this planet of ours. So thank you very much for coming, all of you. Thanks for watching. We hope to see you soon.
One comment.
Yes.
But do not miss the opportunity to go to Starmus Festival next May. Yes. I've been attending several of these festivals in the past. And for example, the last one in Armenia, it was a mix of science and music. It's absolutely fantastic because, for example, in Armenia, we have several thousand of people every afternoon and night attending. It's not only astronomy or astronautics. It's biology, it's oceanography, it's very different domain. And evidently it's not for specialists, it's really for general public. And I'm really fan of this thing. And not only because Garik.
Thank you. Nice.